Hi, everyone. All right, so let's talk kinematic equations. Now, we've already covered distance, displacement, velocity, speed, acceleration. We've talked about the first three formulas on your reference table. The problem is we can't use only those three formulas to solve every kinematic problem. So we need to jump in and talk about some new ones. So let's get into this PowerPoint. Okay. So as far as kinematic equations goes, you should have your new packet out in front of you so you can follow along with your notes. So let's review. So we have our average velocity formulas. V average is equal to the change in your displacement over the change in your time. We also have another formula for this where you add your initial and final velocities, divide them by 2. Again, think about when you want to find the average of test scores, you take as many values as you have and divide by that total. Or the total amount for that matter. Okay. So these equations are only good if you're wanting to talk average velocity. We have something that we call instantaneous velocity, which is the velocity at that moment, which we can't use these two equations for because it only talks about the average. We talked about acceleration. We're talking about acceleration being the change in your velocity over the change in your time, the change of velocity with respect to the change in your time. We came up with the third equation, this one right here on your reference table. So the final velocity is equal to the initial velocity plus your acceleration multiplied by the time. This formula and this formula, these two are the same, remember? The second one here is just expanded upon. So like we said, we can't use only those formulas, so we come up with two new ones. The first is called the distance or your displacement equation, where your distance is equal to your initial velocity times the time plus 1/2 times the acceleration times time squared. In this formula, you have to make sure you are paying attention to first that square. That square is only attached to the t, so the t is being squared, not the whole 1/2 at squared. So make sure that you're being careful with that. You also do have a 1/2 there. My advice, in your calculators, put it as 0.5 rather than do 1/2. I know a lot of you have the fancy calculators with the LED screen where you can actually put in your fractions. If you don't have that, or even if you do, to avoid errors, just put it as 0.5, 1/2, 0.5, same thing. Avoid some errors there. The next formula that you have is the timeless formula. Notice in this formula, the only one that we have here out of these 5 that we're talking about, this one does not have time. So if you have a situation where you are not given time, this is your go-to formula. So you have VF squared is equal to VI squared plus 2 times your acceleration multiplied by your distance or your displacement. Also, in this formula, do keep in mind your final velocity is squared on its own, your initial velocity is squared on its own, and you have to make sure that you're squaring in order to solve. One thing to also make note of, you are not going to be taking any square roots or anything like that until the very end. So square roots, if you take it in the beginning, is going to make a whole bunch of a mess for us, and we don't want that. So we avoid it. So you make sure you take square roots at the very end of your problems. All right. So on the bottom of your page, we have a train starting from rest. What does rest mean? Rest means your initial velocity is equal to 0. So 0 meters per second. Remember, we don't leave naked numbers. We make sure we put units for everything. So VI is equal to 0 meters per second. It leaves Greenberg Station and travels for 500 meters with an acceleration of 1.2 meters per second squared. Okay, so we're looking for the train's final velocity. Now, we are trying to work with these new equations here. So we have our initial velocity being equal to 0 meters per second. We have 500 meters. Meters is the unit for distance, so we have d is equal to 500 meters. We have an acceleration of 1.2 meters per second squared, so a is equal to 1.2 meters per second squared, and we are looking for the train's final velocity. What don't we have? We don't have time. Therefore, we are going to use our timeless equation. Now, I know that we can do the math I know that we can plug in numbers and do the math for it. We are going to do a ton of practice with this tomorrow as far as plugging in and solving and all that stuff. But for now, it's important to just kind of get familiar, we'll say, with the formulas. So now we have your final velocity. We want to know how long does it take the train to reach its final velocity. Well, now what are we looking for? We're looking for how long it takes. So we're looking for the time. At this point, you have every single given rather than time. So we can use really any other formula. Now, the easiest one to use to be able to plug in is this one, our VITAT formula. Remember, VITAT, VITAT, just a shortcut of being able to do that. So we have VITAT, 34.6 meters per second. Make sure you're putting in your units there. Units are important. Units, not putting units, rather, take away your points. 0 plus 1.2 meters per second squared multiplied by t. Remember, in acceleration, meters per second squared is your unit. It's not actually squaring your acceleration. So we go through, we solve, and we get 28.8 seconds. What happens if you were to get a negative time? You need to redo that problem. You can't just get rid of that negative. That's not proper physics. You need to get rid of that negative by actually redoing the problem, seeing where you went wrong. So just keep it in mind. All right, let's try one more. A driver traveling at 85 miles per hour sees a police car hiding in the trees 2 miles ahead. He applies his brakes, decelerating at negative 500 miles per hour squared. Okay, couple things to note here. We work with meters per second. However, we can use miles per hour as long as your time is in hours. As long as the units match, that's totally fine. In acceleration, if we were talking about deceleration, we do indicate it with a negative. So that's where your negative 500 miles per hour comes from, miles per hour squared. If the speed limit is 55 miles per hour, will he get a ticket? Well, okay, what do we know? We know that the driver is traveling at 85 miles per hour. So that is your initial speed or initial velocity. He sees a police car hiding in the trees 2 miles ahead. 2 miles is your distance. He applies his brakes. Therefore, he's decelerating, which means that he's slowing down at a deceleration of negative 500 miles per hour squared. We want to know, will he get a ticket if the speed limit is 55 miles per hour? Well, we need to know what is his actual speed traveling with this deceleration. So we need to find out what is his final velocity. Okay, we're going to go through, we're going to solve this. Now, one thing to keep in mind here is you do not have what? You're not given time. So again, we're going to use your timeless formula and we are going to plug that right in. And I'm going to give you a second here. I want you to stop the video, pause it for a minute. I want you to plug it in and solve it on your own before I click that button and show you what the actual answer is. Does he get a ticket? Does he not? Pause it. You solve it. See what happens. Okay, so hopefully you pause this video. Hopefully you got an answer, the correct answer, which is yes, he does get a ticket. He would be traveling at 72.3 miles per hour. And there's your work for it. So do make sure you go through and check that out. Remember, you are not square rooting until the very end, or else you are not going to get the correct answer. Also, do note that this square here over the for your initial velocity is on the outside of your parentheses. Keep it in mind. So the answer is yes. What would his acceleration need to be to not get a ticket? Well, you need to know what does his acceleration need to be. Okay, well, again, I don't have time. So we can't use any formula that has time. So pause this video again, solve, see what is his acceleration, what should it actually be? All right, did you pause the video? I hope you paused the video and you're not cheating here. Okay, so we should have used your timeless formula. Here is the work for it. You should, of course, get a negative acceleration because he should be decelerating. If you got a positive, well, that doesn't make any sense. because if he's accelerating, then he's not going to be slowing down, right? So we get negative 1,050 miles per hour squared as his deceleration. You have a couple problems on this page right after this one. On this page, you have problems 1 through 4. What I want you to do, as I told you in class, is go through here and I want you to solve 1 through 4, making sure you're paying attention to those signs and those problems. Solve 1 through 4, and we are going to go over those first thing tomorrow. See you then.